All right, so we're good to go. All right, so something up front I wanted to mention. I've been for pretty much the whole time I've been at Clark. I've been recording my lectures and posting them on YouTube for students to look at. And by and large, students have found this useful because, my goal is when you're in class, you can be thinking about what we're discussing. You can be asking questions, trying to understand the material instead of trying to write down every word that I say or copy every picture I draw. So the videos are posted, and you can go back and you can look at those, and not have to worry about taking notes. In class, you can write down the things that seem useful to you to write down, but you don't have to worry about copying everything that you see during the lecture. So usually students appreciate this, but there are privacy concerns associated with this. So I, to the best of my ability, I try not to show student names during lecture. What you're seeing when I share my desktop is basically what goes into the video. So I don't show student names. My chat window is off to the side, and so on and so forth. And if I mess up, I usually stop the recording or go back and edit it out. So the school sent out a note yesterday saying that if we record students asking questions, right, speaking, that can be considered a privacy violation. So I want people to be able to ask questions. So here's what we're going to do. If you have a question that you want to ask during lecture, you got a few choices. And I'm going to pause my recording for a moment. All right, so if you look under participants, you'll see two entries for me. One is just Nick Macias, that's me lecturing to you right now. The other is Nick Macias questions. If you want to ask a question and you don't want to speak out loud, go ahead and send me a private chat on to Nick Macias questions, okay? That's running on my phone in front of me. Eventually I will see that. If you don't want to do that, you can just go ahead and ask a question, but tell me that you don't want it recorded. I will go ahead and note the time, and I'll take it out of the recording before I post it. Okay? So two options. Either send me a private message, and I will read the question to the class and then respond to it as best I can, and you can follow up in chat, or just tell me that you don't want it recorded, and I'll take it out. So hopefully that makes sense to everybody. You can just talk, yeah. I just want everybody to know that it will be recorded. So cool. All right. So let me talk about the labs and the homework first of all, and then we will talk about the next lab, and then we will play around with some TinkerCAD and see what kinds of things we can do with that. So I'll do some hands-on sharing with TinkerCAD. So labs first of all. So I graded lab 1, I posted those grades, and I recorded comments on Canvas. And that's generally how I'll return the feedback to you, is through Canvas comments, okay? So the labs look really good, okay? This is the first Engineering 250 lab, and by and large, people did a really good job following the instructions in the lab and writing it up. So that was great. So a few general things to keep in mind. First of all, labs are being done individually this quarter, okay, for this class. Some of the stuff on Canvas, some of the write-ups may talk about your lab partner, because normally we do these in groups because we only have so many parts kits and so on. But since we're doing this remotely, right, everybody's supposed to work on their labs individually. Now, if you want to talk to other people about your lab, and problems you're running into, that's great. Collaboration is wonderful. But your lab report is your own, so you don't have to list a lab partner on it, okay? And you don't want to share, pictures and equations and things like that with other people. General comment on lab reports, okay? So the report is really how I know what you did and how you're presenting your results to me. So think about the organization of your report, okay? Think of it as not just a homework assignment where you just try to fill in, all the pieces that are asked for, but make it a document that you could read start to finish, and it tells a consistent story. So, put a cover sheet on the front with your name, Engineering 250, the date, the lab number, maybe, a few words about what the lab was, like, traffic intersection circuit or something like that. And then, a sentence or two of introduction. In this lab, we used TinkerCAD, got familiar with different things we can do with that. We looked at protoboards and we started a design for a traffic intersection, right? Something like that. It doesn't have to be formal. It doesn't have to be fancy wording, but something that just describes the lab. And then for each experiment, experiment 1, tell me what you did. Use complete sentences, okay? In this experiment, we were asked to look at different pieces of TinkerCAD and see what things can be changed. For resistors, we can change the resistance value. For wires, we can change the color, and so on. If you have pictures to put in, and most people put pictures in, and that was great, right? Pictures really are a good way to convey information. If you have pictures to put in, try to make them very, very clean copies, okay? If you're using TinkerCAD, you can take a shot directly from the screen. You can use a clipping tool, Orphan View, print screen will usually put it on your clipboard, right? So try to get a nice clean copy. If you want to write things up by hand, circuit diagrams, some equations, right, are easier to write by hand, go ahead and do that. But I ask you to write very neatly as if you were turning this in on paper. Try to get a clean picture of it. Try to make it, as large and high resolution as possible. And if you've got 5 things on a piece of paper and you only want to talk about one of them, don't put on a picture with 5 things in the middle of the lab report, right? Use a cropping tool, pull out the section that you want, put that in your lab report, and then talk about it. So that when you're talking about the truth table, the thing right above or below that is the truth table, as opposed to, the picture of the intersection. So just think about organization, right? The reports are looking really good, so we're just going to keep improving them as we go through the quarter, so that by the end of the term, these are very high quality reports, and this will work really well wherever you go after this course and after Clark. All right, so let me talk about some specifics with Lab 1. So the traffic intersection, we sketched this out last week. It looks like this. This is west, this is south, this is east. Okay, I didn't take off points if you call these A, B, C, or 1, 2, 3, but I will take off points next time. Okay, so I want you to refer to these as west, south, east. And we have 3 sensors. Okay, so there's a sensor here, and here, and here. And you should have 6 lights. Okay, so 3 sensors. 1 to tell you if there's a car in each of the 3 lanes, and 6 lights. If you only did 3 lights, that's a problem, okay? Yeah, we can have 3 LEDs and we can turn them on or off, right? But that's not what we're supposed to do. We're supposed to have 6 lights, 3 greens, 3 reds, okay? Which means that your system diagram should look something like this. 3 inputs for the sensors, 6 outputs. Okay, and then label these using, west, south, east. So usually most people will just call the inputs west, south, east, and they'll call their outputs something like, green west, red west, green south, red south, green east, red east. Or maybe west green, west red. But something, that corresponds to this picture. And then you've got to tell the person looking at the system diagram, what do the inputs and outputs mean? So for example, 1 means car, 0 equals no car. 1 equals on, 0 equals off. Okay, those pieces of information together with this tells somebody who's using your circuit exactly how to hook it up. If they have a car sensor that shows 1 when there's no car, they have to invert it and then connect it to these lines on your circuit. If they have lights that turn on when you feed a 0 into them, they need to invert those, and so on. Okay, so you want picture the intersection and a system diagram. And system diagram is going to be a part of pretty much everything you do from here on out in the lab. You're always going to want a system diagram. And then the truth table, you can tell what the truth table should look like by the system diagram. Since we have 3 inputs, you should have 3 input variables, and you're going to have 2 to the third, or 8 combinations of inputs. And since you have 6 outputs, you're going to have 6 output columns. And the order of these don't really matter, but traditionally when you write a truth table, the order in which you list all the combinations goes in this order, so that if you converted these to integers, it would be 0, 1, 2, 3, 4, 5, 6, 7. Technically, the truth table is correct no matter what order you list these rows in, but this is the way that'll keep things from getting too confusing. For sensors, are we supposed to do logic gates or not? You're designing the system diagram. Well, I'll have to look at lab 2. Let's see when we get there, because I haven't actually jumped into that yet. Let me go ahead and just take a look at lab 2. Because I don't know if you want to put switches on there or not. So, schematic for your design. Yeah, so you're going to want to list switches for the lab. So when you're actually designing the circuit diagram, when you have an input, you'll want to do something like pull it up through a 1K resistor and use a switch to connect it to ground, and label this, say, west, for example. And then that goes into, you know, whatever logic you have. So the sensors are simulated with switches. The lights are simulated with LEDs. So there's not actually logic gates per se for this, but there is circuitry. All right, so truth table should have 3 inputs, a total of 8 rows, and then 6 outputs, a total of 6 columns, which will be a total of 48 ones and zeros over here. Okay, and just fill it in based on this. So rules of Washington, and the setup for this is basically if there's a car sitting here, they get a green light, everybody else is red. If there's no car here, but there is a car here, then this car gets the green light, even if there's someone to the west. If there's no car here or here, but there's a car on the west, then west gets a light. If there's no car anywhere, you can either pick a lane to turn green, or you could make them all red. Okay, but absolutely you should never have more than 1 light green at a time. Okay, so that's kind of a second check on your truth table. All right, other thing on the labs is make sure you have, you know, a section for lessons learned or conclusions, and then have a new experiment. And your new experiment, you have to describe enough detail so somebody can do it. So you can't just say, let's do a 4-way intersection, right? What does that mean? What are the rules? How do you control the lights? When do they turn green? Who gets priority? And so on and so forth. You've got to spell that all out. Okay. And then on the homework, I got homework graded and turned in, and the homework looked good. A lot of hard work in there and a lot of good answers, so I was really happy with that. Same general comments. Again, try to organize it logically, right? I'm going to ask that you work down the page and not across. So if you're trying to do a problem, and let's say this is the page that you're writing on, you know, here's question 1A, and do that. And here's question 1B, and do that. And here's question 1C, and do that. As opposed to, you know, putting question B over here, and then, you know, going up here for D, and so on, right? So just work straight from top to bottom. And if there's multiple things you have to do, move down the page, right? So I graded question 6, which was doing some calculations using 2's complement. So here might be a way that you could write this up. So let me pick on, you know, 6D. Okay, so the question is 119 plus negative 17. Okay, and you need to convert 119 into decimal. So if you want to put some work over here, I'm okay with that. So 119 divided by 2 is 59, remainder 1. 59 divided by 2 is 29, remainder 1. And so on, right? And when you finish up all of this and you find what 119 is equal to, it's like 0, 1, 1, 1, 0, 1, 1, 1. Okay. Think of this as scratch paper, right? Off to the side. Over here, what's the conclusion of that? 119 equals 0, 1, 1, 1, 0, 1, 1, 1. Okay, what is negative 17? Well, 17 is this, and if you complement everything, you get this, and if you add 1, you get this. Okay, that's negative 17. Put that down over here. Okay, you're presenting an argument basically. You're telling the person reading this, what are you doing? Here's 119, here's negative 17. Add them together, and 1 and 1 is 0, and there's a 1, and 1 and 1 is 1, and there's another carry, and there's a 1, which is 1, and you get 1 and 1, and I probably got off by 1 somewhere. But you know, go ahead and do that, and then you know, say this thing equals 102, right? And circle your answer. Okay. So the goal is to work logically from top to bottom, right? And if there's scratch work that you have to do, like doing these calculations, best possibility would be just put them right in line, right? But you know, if you don't want to spend a whole page of paper to do that, right? If you want to put scratch work over here on the side, that's fine. But top to bottom, that's the stuff I'm going to look at. Okay, just think about the organization of it in those lines, and that's great. The other thing, right? Pictures have to be, you know, clean pictures that are legible. You're welcome to write this stuff by hand. Typing this in takes a long time. Okay. And I want to see your work, right? If you just show me this, right, and I don't know how you got 119, I don't know how you got negative 17, right, you're not going to get full credit for it. You may not get any credit for it, right? On a test, you probably wouldn't get anything because you got to show your work, right? But doing this kind of thing, typing it in, really hard to organize, go ahead and write it up on paper. Yeah, because typing takes a long time, right? And I'm totally fine with handwritten stuff. Just write it, you know, as neatly as you can. Take a clean picture, paste it all into a PDF. All right, so hopefully that makes sense. Let's see. All right, let's go ahead and look at Lab 2 for real. So Lab 2, number of pieces to this. So what are we doing? We're playing more with logic gates. We're playing with different ways to connect LEDs and resistors and gates together, and switches, right? So these are the building blocks we'll use for most of the circuitry we build in this course. So experiment 1 is about LED usage. And LEDs, you know, they're these funny little devices that you run current through and they light up. So I'm going to go ahead and do TinkerCAD while we're talking about this and just kind of show you some things with TinkerCAD, which loves logging me out every day. Alright, so you're going to come over here to circuits. Maybe. And I'll create a new circuit. And I'll just call this Lab 2. And remember, come over to Basic Components. Select All, because there's some basic ones that you won't get otherwise. So I'm going to grab a proto board. I'll just grab a small one. And as somebody pointed out in chat, we need to use a power supply to drive these, and a lot of the videos use Arduinos to drive them. We were trying to put together kits that students could use at home during COVID-19, so we were going to power those with Arduinos. So I think that's why some of the videos look like that. Okay, so here's a power supply. And I'll put it over here on the side of my table, and let's just get an LED. Okay, so there's an LED. So you probably got some of this in 120, but let's just review, right? So the power supply basically puts out ground and power. As you know, the connectivity of these boards is such that this horizontal line is connected, this horizontal line is connected, same with these two on the bottom, and then each row of 5 is connected vertically. So one way to wire your board together is draw a wire from the negative connection to ground. And sometimes it's nice to color code these, so black wires are traditionally ground and red is traditionally the one carrying the voltage. So run that over there, and let's make that wire red. And if you color code these, it makes it a little easier to avoid you know, hooking things up to the wrong places. And it's nice to have power available at the bottom of your board as well as the top. So typically we just run a connector that connects the ground, the power rails on the top and the bottom. And this is useful when we start wiring up chips, because chips need, you know, ground on one side and power on the other. So now anytime that I want a ground connection, I can connect to this line or I can connect to this line. And for 5 volts I can connect here or I can connect there. Okay, so that's just a bit of a convenience. So let's drive this LED. Okay, so we're told for an LED the straight pin is negative and the one that's got a bend in it is positive. So this line right here should be connected to ground, and this line here should be connected to power. And if I do that and I start my simulation, my LED lights up, but it actually explodes, right? Because we're running too much current through it. Look at my power supply. It says it's putting out 403 milliamps, 483 milliamps. That's half an amp, okay? That's enough to power a cell phone. And this LED can't handle that much current. So it's showing you a little explosion symbol there to say, you know, there's too much current. And if you put your mouse over that, it's really small, but it says absolute maximum current is 20 milliamps. Okay, so let's stop the simulation. Let's put in a resistor. So I'll drag a resistor over here. I'll take this wire and move it down like that. And I'll put the resistor over here. So what have I got now? I've got 5 volts. I've got an LED. And the default resistor value is 1 kilo ohm. So 1 kilo ohm, but you can set that however you want. So the ground goes through a resistor into the ground end of the LED. The positive end of the LED goes to the positive end of the power supply. So we've built a circuit like this, which is a correct way to wire up an LED, right? So if we run that, we get a nice, nicely lit, and it says it's drawing 3 milliamps. All right, so you can play with LEDs. The first experiment asks you to wire up 3 different circuits, okay? This inverter, this is a 74 LS04, okay? That's a hex inverter, so it has 6 inverters inside. And you can pull up the data sheet and look at that and see where the inputs and the outputs are. We looked at this a little bit last week, so let's go ahead and just put an inverter on our board and see what happens. So 74LS04 is a hex inverter. So we'll drop that in here. So L means low or 0, and H means high or 1. So yeah, when you look at the data sheet, sometimes you see 0, 1, sometimes you see L and H. Just means 0, 1, low, high, 0 volts, 5 volts. And so if you look at the data sheet, pin 7 needs to go to ground, and pin 14 needs to go to power. So we can wire it like that. And now, instead of driving the LED from the power supply, let's drive it from pin 2. And let's take a wire from pin 1 and connect it to ground. So now we have an inverter with the input receiving a 0 because it's going to ground, and the output going to an LED, and the other end of the output going through a resistor to ground. So now our circuit looks like this. We've got a ground or a 0 going into the inverter, right? This is pin 1. The output is on pin 2. That goes through an LED, a resistor, and goes into ground. So input to pin 1, output to an LED, and then the other end goes through a resistor into ground. So if we run this, the LED lights up. Why? Because when you put a 0 into an inverter, you get a 1 coming out. And a 1 over here, or ground over here, that causes current to flow. But if I were to take that input and connect it to a logic 1, which is VCC, the LED is off. Because now I have a 1 coming in here, that's a high voltage. It gets inverted to a 0. I have 0 volts here, 0 volts there. There's no current flowing. So that's the kind of thing you're playing with in experiment 1. Okay, just looking at these different circuits. These chips can get exploded too. I did this accidentally the other day. I turned my power supply up too high, and you'll get a little explosion symbol there. It says the maximum value is 7 volts, and it really should be 5 volts. So, and it doesn't do any harm here. If you do this in the lab, you actually smoke the chips. And the only possible downside to that is if you accidentally touch it when it's connected like that, it can get really hot really fast. But, you know, on the simulation, we can play around with this stuff. All right, so that's experiment 1. You're going to build these 3 configurations, and you're going to observe what happens and try to explain why whatever happened, right? If the LED is on in this case, why is it on? If it's off, why is it off? Okay, so it's an experiment and then a thought experiment to try to explain what you observed. Okay, experiment 2 is about hooking up switches. This is this configuration of switches that we keep drawing. Take an input, pull it through a 1K resistor up to 5 volts, and then use a switch to connect it to ground. So this arrow up here, that means 5 volts, or whatever your power supply is. This big triangle, that means ground. So that's VCC, 5 volts. That's ground, that's ground. Those are both LEDs, and these are both inverters. So build this circuit, and when the switch is open, which is the position it's in right now, right, where there's no connection, see what happens to your LEDs. And when the switch is closed, which is when you're making a connection between this side and that side, see what happens to your LEDs. And make a little table, okay? So make a table where your input is the switch, and 0 means closed, 1 means open, and the output is 2 columns, an output for L1 and an output for L2. And on the output, if the LED is off, record a 0. If the LED is on, record a 1. So make a truth table for this circuit and see if it makes sense. Okay, experiments 3 through 5, you're building more circuits. So in this case, you're using a chip. This is U1 is 74HC08. I say LS, it's the same thing as HC. So this is a 7408 chip. Build this circuit. Okay, you've got a pair of switches going into pins 1 and 2. You've got an output from pin 3 going through an LED and a resistor to ground. Okay, you've also got pin 7 connected to ground. Pin 14 should go to VCC. And this is a typo. Do not connect pin 6 to pin 7. Okay, that should not be there, so make a note of that. Okay, don't connect pin 6 to pin 7. So make a table out of this, right? Again, if the switch is open, that's a logic 1. If the switch is closed, it's a logic 0. So go through all combinations of the switches to give you all combinations of inputs A and B, right? So make a truth table with A and B listed like this. List all the combinations. And for each of those, record what the output is. If the LED is lit, the output is a 1. If the LED is not lit, the output is a 0. So make that truth table, and then look at the data sheet for 74HC08. See if that truth table that you got matches what it should do. Okay, do the same thing for a 32. Do the same thing for an 04. All right, so those are all TinkerCAD experiments, and they have a component where you're trying to explain something about what you're observing. All right, and then experiment 6 is the next piece of the traffic control signal. So same traffic control signal. Go ahead and resketch the diagram of the intersection. Okay, label the input and output variables. And if you already did this correctly in Lab 1, you can take exactly the same picture. That's fine to reuse it. If you want to make changes to it, go ahead and redraw it. System diagram, same thing. You can reuse or you can redraw. But make sure you list 3 inputs, 6 outputs, and specify 1 means this, 0 means that for the inputs, and 1 means this, 0 means that for the outputs. And then the truth table, right? And if you need to make changes to it, make changes and write up a truth table with 3 inputs, 6 outputs. And then the new piece is a schematic for your design. Okay? So your schematic is going to look something like this. Okay? It's going to have some chips in it, but no, it does not look like this. It's going to look something like this. Draw logic gates. Right? If you want an AND gate, draw a symbol for an AND gate. Label these things, you know, U1, U2, and so on, and specify what these things are. So this is what we looked at last week for drawing a circuit diagram. So don't draw a picture of the chip and wires going to the individual pins. Okay? Draw a logic diagram like this. Label the pin numbers, though, right? For where they would get connected to wires. Put in LEDs for your output. Put in switches for your sensor inputs. Okay, so you don't need truth tables for the sensors. The sensors are just switches. Okay, but the circuitry that's connected to the sensors, which is your whole circuit diagram that implements your truth table, that's what you're drawing a truth table for.
So there's software on the Engineering CS website. It simulates circuits. I forget what it's called. Are we allowed to use that for our schematics?
Yes, you are. Yeah, it's Logic Sim or something like that. So you can use software to sketch the circuit diagrams if you like, but you're very, very welcome to do them by hand. Okay, if you want to do them by hand, I strongly recommend getting a nice sharp pencil and a straight edge, and just work neatly, right? Sometimes you can work directly on graph paper, or you can throw a piece of graph paper under a plain sheet of paper. And for me, it's kind of meditative and fun to use templates and straight edges and draw things like that. So whatever works for you, okay? And it's helpful to have something that you can draw on, so that while you're wiring up your circuit, you can, for example, highlight the wires as you place them. That can be useful too. All right, so draw a schematic for your design, and you can only use the 74HC devices that are available in TinkerCAD. Okay, so in particular, these things down here. So there's a 3-input NAND gate and a 3-input AND gate, a 4-input NAND, a 3-input NOR, a 4-input AND, but I don't know if we have, so there's no 5-input gates, and I don't know if there's a 3-input XOR and so on. So make sure that anything you're putting in your picture corresponds to a chip that's available on TinkerCAD, because in the next lab, lab 3, you're going to actually build your circuit and simulate it in TinkerCAD. Okay? For this lab, you're not building your circuit, you're just sketching the diagram. Okay, so you don't have to actually build it, but you're welcome to, of course, if you want. All right, any other questions about lab 2?
I was wondering, what do you mean by cross-schematic? Like a difference between diagram.
So a schematic would be, here's my West sensor, and it's a switch, and this goes through a 1K resistor to 5 volts, and this goes to ground, and maybe this goes through an inverter, and maybe this goes into an AND gate and gets ANDed with something, and maybe this goes through an OR gate, and there's another switch over here which is south, and another switch over here which is east, and you've got all this stuff, and at some point there's an LED which is labeled green west. And at some point there's an LED which is labeled red south, and so on. So the full schematic for your circuit, right? Something that you could use to actually build your circuit just by looking at this picture. And when you have gates, I do have dogs barking. That's not the worst of it here usually. So when you have gates, right? Label this, for example, this is U1, this is U2. If I have another inverter down here, that might also come from U1. U1 corresponds to a physical chip. So up here in the upper right corner, you put your component ID block. So you have the ID, you have the part, you have where ground is connected, you have where VCC is connected, and where you have no connections. So U1 might be a 74 HC04, and ground is on 7, VCC is 14. And maybe I'm going to hook this one up to go in on pin 1 and 2 and go in on 3 and out on 4. And if those were the only pieces of U1 I was using, then I would have no connection on 5, 6, and 8 through 13, for example. And then U2, which is a quad AND gate, would be a 74 HC08, and so on and so forth. Right? You don't need to list switches, resistors, and LEDs up here. This is just for integrated circuits for chips, right? But the idea is, you decide where you're going to connect these things to on your chips, so that somebody can take this and they can build your circuit.
Okay.
So making a schematic takes a lot of time. All right, but it's time really well spent, because particularly in the lab, usually you find students struggling with circuits. They have a protoboard with wires all over the place, and their circuit's not working, and they have no idea why. If you have a picture like this, right, neatly drawn with everything labeled and all the pin numbers labeled, you can flip this switch and say, I should be getting 5 volts out of this point right here. It's U1, it's a 7404, it's pin 2, you can go right there and take a voltage reading. And if you're not getting what you need, there's a problem with the inputs. Now you can go right here and take a voltage reading, and it makes it really easy to debug circuits. So drawing a good schematic is an essential skill for making these things doable. All right, and then again, lessons learned, new experiment, cover sheet on the beginning, and you're good to go. Submit it as a PDF. So I haven't seen many people in office hours this week, but you know, I've got hours 11 to 12 for this class, Tuesday through Thursday, 8 o'clock most mornings, 7 o'clock Wednesday mornings. If you need help figuring out how to bring images into a document or export, or you know, using a cropping tool or things like that, we can always do that through Zoom. Okay, so I'm happy to help people with logistics of, you know, how to do some of these things to turn them into pieces of a report.
Professor,
Yeah.
For experiment 1, 2, and 3, could you go over those? The H kind of throwing me off. Just understanding.
L means 0, so connect this to ground. H means 1, connect this to 5 volts.
All right, thank you.
That's all it means, and I think that's yeah, it's the same here. Yeah. Can anybody hear me? Somebody's asking in chat. And I'm guessing people can because you responded to me.
I can hear you.
Okay. All right, so switches in TinkerCAD, this is the last thing I want to look at in TinkerCAD. There's these little collections of dip switches that you can bring in here. And the way they work when you're running your simulation, you can click on these switches to slide them up or down. When you slide them in the up position, they will make connection between here and here. Yeah, I get email messages or pop-ups on my screen constantly saying internet connection is unstable, and I think it's just a Zoom thing because it doesn't seem to be a problem. So when the switch is in the side that says on, then you have a connection between one side and the other. So that corresponds to a switch that you've, right, this would be off. And if you press the switch down, this would be on. And so you can interact with your circuitry like that. So typically you would pull one end up to 5 volts through a resistor, and then you can feed the other end. And let me just go ahead and do that just for completeness sake. So let's take switch 1 and let's use that to drive the input of our gate. So I'm going to pull it up through 5 volts through a resistor, and then the input of the gate I'm going to take from this end, and then the bottom of the switch I'm going to connect to ground. So I've just wired this up as follows. I'm drawing a picture and then I'll show you. So I've wired this up as a connection to ground, a switch, the other end of the switch going through a 1K resistor to 5 volts, and then this going into an inverter, and then the inverter goes through an LED, and that goes through a 1K resistor into ground. So this is the circuit we've got on the proto board, right? The same inverter, LED, resistor, ground connection we had before, but instead of just connecting this directly to ground or 5 volts, I'm using a switch, right? If the switch is open, this will go through the resistor to 5 volts. That's a logic 1. If the switch is closed, like this input's connected directly to ground. That's a logic 0. So if we simulate this, right? Right now the switch is open, is on, right? Which means we're connected to ground, so the input to the inverter is a 0, which means the output is 1, so this LED is actually lit. If I flip the switch, the LED goes off. Okay, because when the switch is off, when it's open, the input goes to 5 volts, that's a logic 1 or a high. the output is logic 0 or low. So when the switch is in this position down here, I'm feeding in a 1, the LED is off. When I move it, the LED turns on. So those are the pieces you're going to use for pretty much the whole lab, except for the last experiment, which you're not building on here. But for the other experiment, it's basically some chips, switches, LEDs, wires, resistors. All right, I think that's all I needed to say about TinkerCAD, so I think we are ready to go on, unless there's any other questions on any of that. All right, let's do a 5-minute break to stretch our brains, and then we'll start talking about the material in Chapter 2 in more detail: sum of products, products of sums, and minimizing equations. So I'll stop the recording for now, and I'll be back in about 5 minutes. All right, so I'm back. Do we take screenshots of circuits to put in a document? Yeah, that's probably not a bad thing to do, but that does not take the place of a schematic. Okay, if you want to include it, I'm okay with that. I think Izad takes off points if you put in pictures of your circuits in the physical lab, but I'm okay with it because it's just a PDF file, so it doesn't cost paper or anything. But make absolutely sure that you also have a schematic if you're required to have a schematic. And when you're writing your lab report, right, remember your lab report is a standalone document. So if you're doing experiment 1, right, if your write-up says, you know, configuration 1 LED was on, configuration 2 LED was off, that does not make any sense to the person reading a report unless they know what configuration 1 is. So you want to include, you know, this picture in your report showing what configuration 1 is. And don't just include it, right? Make sure you say in words, you know, in this experiment we built the following circuit. Show a picture of the circuit and say when we applied power the LED did such and such, right? And then explain the reason why it did that. Next, we built the following circuit number 2. Show a picture of circuit number 2. Okay, that's what I mean by being a self-contained document. Don't assume the person reading it has done this lab or knows about this lab or knows anything about the course. So anytime you talk about, you know, the output was high when A and B were both 0, right? Somebody's going to read that. They have to know what A and B are while they're inputs to the circuit. What circuit? This circuit. Put this picture in your report. Okay. Now you can copy this from the PDF and just paste it in, right? But if you do that, put a note on there saying, you know, picture taken from, you know, Engineering 250 Lab 2.pdf. Okay, cite your sources, because there's no need to redraw this yourself. But don't just put it in your report with your name on it. Make sure you mention that you got it from somewhere else. So that's just stuff to keep in mind, and we'll iterate on that as we go through the course. All right, any other questions? All right, so let's jump into the Chapter 2 material a little deeper, and this is heading towards the Chapter 2 homework. So I put a note on the Chapter 2 homework on Canvas for some changes to 2 of the questions. One of the questions you can skip, and one of the questions you only have to answer part of. So make sure you look at the assignment in Canvas. So we're talking about truth tables and how to go from truth tables to equations. This is our main object of concern this week. So let me close out of here. How do we go from equations to truth tables? And we saw an example of this last week, right? We were playing with a circuit that would unlock something. And so I'll just pick on a function with 3 input variables. And let's just call them A, B, C. And we know there's 8 combinations of those. And I'll just work with a single output for now, but if we had multiple outputs, we would have multiple columns in our truth table. Let's just think of one output called X. And the idea was, if there were certain values where we wanted this output to be a 1, we could look at the input values corresponding to that, and we could write an expression. We could write an expression that was equal to 1 when exactly A was 0, B was 0, and C was 1. And the trick we found for doing that was to think of A bar is equal to 1, and B bar is equal to 1, and C is equal to 1. And so the expression A bar ANDed with B bar ANDed with C corresponds to this second row of the truth table. And if we were to just evaluate this expression, it would correspond to a truth table that had a single 1, which was right here. Because when exactly A is 0, B is 0, C is 1, this is 1, this is 1, this is 1, the AND is 1. And in any other row, at least one of these terms is going to be 0, so the AND will be 0. And so this term corresponds to A, B, C bar, and this corresponds to A, B, C. So if we wanted to write an expression for this X based on this entire truth table, it would simply be the OR of those 3 expressions. A bar, B bar, C, or A, B, C bar, or A, B, C. So given a truth table, we can write an algebraic equation, a Boolean equation, that will match exactly that output of the truth table. This expression will be 0 in all cases except where ABC is either 0, 0, 1, 1, 1, 0, or 1, 1, 1. And this is called a sum of products representation. Usually just SOP. So when we do ANDing, right, and we just write our terms next to each other, it kind of looks like we're multiplying them, right? That's called a product. Okay, a product is synonymous with the idea of ANDing. And if you look at a truth table for just an AND operation, the truth table value is exactly the product of the 2 inputs, right? 1 times 1 is 1. 1 times 0 is 0, 0 times 1 is 0, and 0 times 0 is 0. So ANDing and multiplying kind of look the same. So the term product refers to doing an AND. So this is a product, that's a product, that's a product. And our expression for X is the sum of those. So summing is a synonymous term for ORing. And the truth table for an OR almost looks like addition, but not quite. But nonetheless, when we OR things together, we say we're taking the sum of them. So this is a sum of 3 products. Product, 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 sum them together. So any expression in this form, product term plus a product term plus a product term, that's called a sum of products, SOP. And we can always write a sum of products from a truth table by just following this trick. All right, if you're still with me, we can simplify this. Because if I give you a different truth table, it's going to be exactly the same procedure, right? I might call these things, you know, RST instead of ABC, but it would just be R bar, S bar, T, or RST bar, or RST. Just changing the variable names, that doesn't do anything. And if I move this 1 down here, right, well, this is just going to be, you know, A bar, B, C bar. So we can standardize this. We can take the thing that we're doing and put it in sort of a packaged form so we don't have to reinvent this every time that we want to take a truth table and come up with an equation. So we're going to start introducing some symbology and some terminology. So let me make my general truth table again. And I put this bar to separate groups of 4 only because it helps me draw straighter lines. It doesn't mean anything beyond that. So this always corresponds to the term A bar, B bar, C bar. This is A bar, B bar, C, A bar, B, C bar, A bar, B, C, and so on. Now I don't have these memorized, but I'm using a trick. If I have a 1, I write down the variable. If I have a 0, I write the variable with a bar on top. So there's a 1 that's A, there's a 1 that's B, there's a 0 that's C bar, and here I've got all 1s. Okay, these expressions, these products are called minterms. Okay, so a minterm is a product of your input variables, possibly with bars on top, corresponding to a particular set of input values. And so for 3 inputs, we have a total of 8 minterms. And anytime I write an expression like this, I'm just writing a sum of minterms. So for example, in this case where I wanted, a 1 here, here, and here, we ended up writing this equation, x equals A bar, B bar, C, or A, B, C bar, or A, B, C. Well, we use these minterms so often that we make up new symbols to represent them. So this first term, we just write the symbol little m with a subscript of 0. And that means A bar, B bar, C bar. This is m with a subscript 1, 2, 3, and we just keep going to 7. And what that lets us do is write this equation more easily. So let me put my x back in here. So my x was 0, 1, 0, 0, 0, 0, 1, 1. So if I want to write an equation for x, what is it? It's just a sum of the minterms where our output is equal to 1. So it's minterm 1 plus minterm 6 plus minterm 7. So now we almost don't have to think. Right? If we have a truth table, just find where the 1s are and just add up those minterms. That's an equation for x. As long as we understand that m1 means, A bar, B bar, C bar, A bar, B bar, C, and m7 means A, B, C, and so on. Now, if I just write this, I don't know what my variables are, so it's hard to go from this back to here. Okay, to make this meaningful, we really want to say x parentheses A comma B comma C. We want to list the inputs in whatever particular order we want is equal to m1 plus m6 plus m7. And now we've got a really solid expression that we can use to go directly back to this original one or vice versa. Because I listed these inputs as A comma B comma C, I know that when I write a truth table, I'm going to list them in the same order, A, B, C, and I know I'm going to fill out the columns in this standard numbering from binary 0 to binary 7. And so when I see M1, I know it means this second row of the truth table where A is 0, B is 0, and C is 1. And so this M1 now I know corresponds to A bar, B bar, C bar. But you got to have this in here so that you know what the inputs are and what order they're listed in. Because if I listed this as CBA, then the meaning of M1 would change, right? It would be C bar, B bar, A, which is different. Well, this is easier to write than this. But you know, we can make it a little easier. We can use a summation symbol and say, let's just add up M1, M6, M7. Well, the summation tells us we're taking a sum. Anytime that we're doing a sum of terms, and we see, you know, minterms in here, we know it's got to be a sum of minterms. It's a sum of products, right? So these m's aren't actually necessary, and so we can actually write a very compact form of this and just say this is sum 1, 6, 7. And so this is compact form. And it's about the most succinct way to write an equation for x, right? We're really just listing 3 numbers and a summation symbol to say this is a sum of products. And we understand that the 1 corresponds to minterm 1, which we understand because it's ABC, corresponds to A bar, B bar, C, and that we add these up. And so we can produce this original equation just from this compact expression. But this is a whole lot easier to drag around. It's less error prone. We don't have to worry about our bars being sloppy or touching each other or things like that. Okay, so compact form is really nice. And it's a really good form to feed into a computer if you have a program that's processing this information for you. Compact form is very nice. All right, how are we feeling about this? Because we're about to flip it on its head. And it's really no different from what we did in 120. It's just, you know, different terminology, different symbology. Cool. All right, let's look at a different way to make a truth table. So I'm going to do the same 3 inputs and an output x. And suppose my output is mostly 1. My outputs are mostly 1, so I want to output a 1 in most of these cases, except this one right here. All right. Well, let me throw another one in here. We'll just go for it. Suppose you want to output 1s in everything except these 2 rows. Okay, we could write a sum of products. Okay, and if we use compact form, you know, it would be minterm 0 plus 1 plus 2 plus 4 plus 5 plus 7. Okay, that's going to be 6 product terms. That's 6 3 input AND gates, all being fed into a 6 input OR gate. It's a lot of hardware. And yeah, we could simplify this, but if we don't simplify, right, we would end up with 6 terms being ORed together, and each of those terms would have 3 variables. Some of them would have inverters on them. It's a huge number of gates we would need to actually build that circuit. So let's look at a dual way to represent an equation for x in terms of a, b, and c. And this is going to be called a sum of product of sums. And we always see that written as POS, product of sums. So a product of sums is going to look in general like this. It's going to be things added together, things added together, things added together, and then each of those things ANDed with each other. Okay, so each of these expressions is a sum, and then we take the product of that sum, and that sum. Okay, so it's a product of sums. And we want to write a product of sums expression that matches this truth table. Well, if we could find an expression which was 1, which was 0 in this particular row, and an expression that was 0 in this particular row. And if we took the product of those two things, right, if we were in this row or this row, then our output would be 0. Okay, so let's break this down. Let's just look at this row. Suppose we want a 0 in this case. Okay, we want an expression which is equal to 0 when A is 0, B is 1, and C is 1. And it's equal to 1 in all other cases. Okay, we're going to use an OR term. And what we're going to do is we're going to complement our terms when we have a 1 and take them uncomplemented when we have a 0. So just think about this. Suppose I look at the expression A or B bar or C bar. Okay, if I'm in this first row, C is a 0, C bar is 1, this expression is going to be 1. If I'm in the second row, B is a 0, so B bar will be 1, so the OR will be 1, X will be a 1. If I'm in the third row, C is a 0, C bar is 1, the OR will be a 1, that's still a 1. But if I'm in this special fourth row, A is going to be a 0, B is a 1, so B bar is 0, C is a 1, so C bar is 0. This is going to be 0, ORed with 0, ORed with 0. My output's going to be 0. And in all these other rows, right, either C will be 0, which will make this true, or B will be 0, which will make this true, or in this last row, A will be 1, which will make this true, right? So this expression will be 0 only in this row, and it'll be 1 everywhere else. And this is called a max term. And there's a max term corresponding to each row. The max term down here is A bar or B bar or C. And I can do the same analysis. If I'm in this row, A bar will be 0, B bar will be 0, C will be 0. This term will be equal to 0. But pick any other row. This row up here, for example, A is a 0, A bar will be 1, the whole OR will be 1. Right? So these max terms are 0 in this particular row and 1 everywhere else. Min terms were 1 in the particular row and 0 everywhere else. Okay, this is a dual, but it does not feel like the same thing to most people. For most people, product of sums is about 3 or 4 times more difficult than sum of products. Okay, this is like KVL, KCL, and 120. Most people find KVL a lot easier than KCL, even though they're exactly the same thing. This is like resistors in parallel versus resistors in series. They're kind of the same thing, but they don't process equally in our brains. Okay, so this can feel kind of wonky. That's okay. We'll get used to it over time. Okay, so there's a max term corresponding to each row, and the max term is 0 in that row. So if I want X to be 0 in both of these rows and 1 everywhere else, what I'm going to do is I'm going to take the product of these two max terms. So if I say X equals A or B bar or C multiplied by or ANDed with A bar or B bar or C, if I'm in a row where this is 0, X will be 0, because 0 ANDed with anything is 0. That's this case right here. If I'm in a row where the second term is 0, the product will be 0. That's this case right here. Any other row, this will be 1, this will be 1, the product will be 1, X will be 1. Okay, so I'll confess that I taught this course for about 2 years before I really made peace with this. Okay, and this was, decades after I got my degree in electrical engineering and theoretically learned this stuff. It's definitely a little strange, all right? But this is a first exposure to it for most of us, and the homework problems are there to sort of help us work with it, play around with it, give our brains a chance to sort of process and grok these ideas. But don't be alarmed, or startled if this is like, what the heck is going on here, right? It's a strange concept, even though, it's in some way the same thing as some of products that we do in Engineering 120. All right, so what can we do with this? If we know the max terms for each of these, we can slap down an equation just by looking for the zeros, writing down the corresponding max terms, and taking their product. So to find min terms, the trick was, if you had a 0, write the variable with a bar. If you have a 1, write the variable without a bar. For a max term, it's the opposite trick. If you have a 0, write the variable without a bar. If you have a 1, write the variable with a bar. And then, instead of multiplying them, right, there's an implicit AND operation in the sum of products. Add them together, take the sum. So product of sums, max terms look like this. For each one, if there's a 1, write the variable with a bar. If there is a 0, write the uncomplemented variable. And there's your max terms. And we want a shorthand for that, so we can label these as uppercase M0, M1, M2, and so on, all the way up through M7. And so we could write X, A, comma, B, comma, C equals max term 3 ANDed with max term 6. And we can shorthand that as the product of max term 3 with max term 6. And we can shorthand that even more as just product 3 comma 6. Sorry, there's somebody doing something in the parking lot. I live on top of a very popular alley, and people with big trucks love to come and park right below my window and run their engines, usually at 4 in the morning. And now they're trying to back into a spot that's about half the size of their truck, but they're doing a good job, and they got 3 people helping them. There we go. All right. That's the adventure part of the lecture. All right, so we can write this very compact form, x of ABC equals just product of 3 comma 6. And once we understand what max terms are, we can say this is max term 3, max term 6. If we know ABC, we can write down, that thing ANDed with that thing. We can reproduce our original expression. So 2 totally different feeling but dual ways to take a truth table and turn it into an equation. One that'll be a product of sums, the other that'll be a sum of products. And when you're first doing this, right, you can get a table of max terms from the book, or you can make a table. But there's a trick we can use for this, right? Suppose we want to know what max term 5 is. Well, write the number 5 in binary, right? And, assuming that we're using inputs A, B, C, write the number 5 in binary. That tells you what the values of A, B, and C will be in that row 5, right? 1, 0, 1. And so for the first one, there's a 1, so write that first expression with a bar. Write the second one without, the third one with a bar, or them together. So M5 equals that. If you want min term 5, if there's a 1, write the variable without a bar. If there's a 0, put a bar. And then AND them together. So you don't need a table, right? You can pull these straight from just knowing how to write this number in binary. But you know, it's also easy just to use the table, particularly at first.
Alright, so in the homework, it would state to tell us either to write in min and max terms, right?
Yes. And let's actually look at the homework right now because I want to make sure we have time for that. And there's a lot we can say about the homework. And it's like 7 pages. All right, so question 1 is just writing truth tables. Okay, so you have a function with 2, 3, or 4 variables, and here's an equation. Write the truth table. So basically, you know, fill out the left side columns of the truth table, and then for each of those combinations, figure out what this expression is equal to and write that in. And it's easiest, to me at least, to do this in parts, right? So say you want to do say we want to do something like this. F of xy equals xy bar or x bar y. Okay, write a truth table, list all the combinations of your input variables, and then break this into pieces. If it's a sum of products, write down a column for each of these products, right? And if you don't want to do this in your head, if you have a y bar, make a separate column first for y bar. Right, so 1, 0, 1, 0. Now I have a column for y bar, I have a column for x. I can write a column for x ANDed with y bar by just ANDing these two columns together. So 0, 1 is 0, 0, 0 is 0, 1, 1 is 1, 1, 0 is 0. And do the same thing for x bar. And then do x bar y, which is this column, ANDed with that second column y. So 0, 1 is 0, 1, 1 is 1, 0, 0 is 0, 1, 0 is 0. And now I can do f, which is xy bar, ORed with x bar y. And all I've got to do is take this column and that column and OR them together. So 0 ORed with 0 is 0, 0 ORed with 1 is 1, 1 ORed with 0 is 1, 0 ORed with 0 is 0. Right? And show all that on your homework, right? Because if you make a mistake here, you know, if I accidentally put a 0 here, everything else is off, right? But I can look at your homework and say, oh, that was just a typo right here. As opposed to, you know, not having any idea what ands and ors are. So, so work methodically, show your work. And these are hard to check, right? But just work carefully. So that's question 1. Question 2, expand this to its canonical sum of products form, okay? So standard sum of products form would be let me see. Yeah, so so something like this, right? Either like that or sum of M0, M2, M3, M4, M6. So you're basically figuring out which min terms you want to have set to represent this function f. So easiest way to do that is to go ahead and write the whole truth table for this, and then just write down which min terms you want the output to be 1 for. All right, question 3, same thing, but you're doing a product of sums and a sum of products. Okay, so you're doing both. Question 4, write the corresponding compact min terms for the following, for each of the functions. So we have 3 inputs, A, B, C, and then we have 3 outputs. Okay, so you're going to write 3 equations, FA equals, and do that compact min terms. So min terms means sum of products. So do something like FA equals sum of, you know, whichever rows you want a 1 to be in. And then write a second equation, FB equals, and a third equation, FC equals. All right, question 5. Each of the following functions is written in a form that is equivalent to the complement of a standard POS, right? So we've written what the complement of this function f is. For each function, write each function in a standard product of sum form and also a standard sum of products, and do it in a compact form. So what's going on here? Well, if you were to write the truth table for this, right, see what truth table this corresponds to. Write that truth table. That's what the inverse of f is. So now if you flip all your zeros and ones, you'll get the truth table for f. Okay, now using that truth table for f, write it in compact sum of product and product of sum forms. Okay, and after you do that, right, look at the original representation of f bar and you'll see something. Okay, you'll notice a pattern. And then do the same thing here, right? The truth table corresponding to this expression, that's the truth table for f bar. Complement everything to get the truth table for f, and then write the sum of products expression for f from that truth table, and then write the product of sum expression for f. And compare your answers, compare them to the original, and see what you discover. All right, question 6, write the expression for each of the following functions in terms of the independent variables. So here you're expanding. Okay, you want to write f in terms of some expression involving a, b, c, d, e. So you're going from the compact form to the explicit form. And we're going to talk about K-maps next. So, and if we don't get through K-maps, I will post a video tonight with what we didn't get through in class. But K-maps are a way that we can minimize an expression so that we end up with something that's simpler. So you'll use a K-map to simplify these expressions. And in 8, same thing. And then 9, I said you can skip. And then 10 will be another K-map, and then 11 we're going to do a K-map for this expression, and I said to skip the SAR part. Okay, well, we'll talk about SAR in class. So sum of products, product of sums that we've gone over is enough to get you through more than the first half of the homework, right, through question 6. And then we want to talk about K-maps next. Alright, and somebody just noted that there's not enough room on a small breadboard to make an intersection, and that is definitely true. But there's big breadboards on TinkerCAD as well.
So we're not doing question 9 in the last part of question 11.
Correct, yeah. You're not doing question 9, and in question 11 you don't have to worry about the SAR minimization. And if you look at homework 2 on Canvas, it's written out in there also. All right, so let's talk about simplification. So here's a truth table. And I'm going to use output values like this. And we'll stick with explicit notation right now. We won't use compact form because I want to actually look at the variables for this. So if I were to write an expression for x, I have a 1 here, which corresponds to the term a, b bar, c bar. And I'm just doing sum of products for now. And I have a 1 in this row, which corresponds to a, b bar, c. So this is a 2-input OR gate, and those inputs are being fed by the outputs of 2 3-input AND gates. Okay, so I need 2 3-input ANDs, I need a 2-input OR. which is, you know, not a lot of logic, but it's a fair bit of logic. It's going to take up some real estate on a proto board. Now, algebraically, we can factor equations, right? This term b bar appears in both of these equations, and this term a appears in both of these equations. So I could factor out this a b bar and just leave c bar ORed with c. And it's just like doing regular algebra. If I were to expand this, this would be a b bar c bar, and this term would be a b bar c, and they get ORed together. Okay, so if we think of this as multiplication and addition, it works like regular algebra. Well, this expression right here is interesting because this term, c bar or c, does anybody know what that's equal to?
It's always true, right?
This is always true. It's not sunny or it is sunny, right? One of those is always true. So c bar or c is always 1, and if you draw a truth table for it, you'll see that anytime, you know, one input is the opposite of the other, that's equal to true. So this is just logically 1. And if we take something and we AND it with true, we just get our something. So x is actually equal to a b bar, which means we can make a circuit that generates x using just a 2-input AND gate. So do you want to use 3 big gates or just one simple AND gate? Probably one simple AND gate. Fewer chips, lower power, fewer things to break, less space, less wiring. Right? It's a win all around. So this is the idea of simplification. And yes, yeah, it is a and b bar. This is simplification. Here's the original equation. Here's a simplified equation. So algebraically, we can do things like this. It's kind of like factoring polynomials, right? So SAR, systematic algebraic reduction, is a technique you can use to go from an equation like this down to an equation like that. I'm not going to go through it because we don't have endless time in this course, and it's not something you're going to do very often. There's a different way that we could get this simplification done, though. So let's go back to the original truth table. And let's think about this truth table in sets of 2 rows. And my 2 1s that I want for my output are in the same block of 2 rows. Okay, what's interesting about this block of 2 rows is that in this row, A is 1, B is 0, C is 0. In this row, A is 1, B is 0, C is 1. Well, if you think about this just a little differently, what you'll see is that in these 2 rows, A and B have the same value. C could be a 0 or a 1. But since in both of these rows we want the output to be a 1, the value of C really doesn't matter. As long as A is 1 and B is 0, the output should be a 1. Similarly, if I wanted my outputs to be 1 here and here, well, as long as A is 0 and B is 0, the value of C doesn't matter. So I could write a simpler term for these 2 rows, which would just be A bar, B bar. So there are these tricks that we can use looking at our truth table if we have a pair of rows adjacent to each other that we want the output to be 1 in both cases. Alright, so we're going to learn a trick. Suppose this is the truth table that we want. Well, you know, I can't do what I just did because my two ones are pretty far apart from each other, right? But suppose I made a new truth table. And all I'm doing is I'm rearranging the order of my inputs, which you can always do. So where do I want my ones to be? A and C are 0, B is 1. So A and C are 0, B is 1. And I also want a 1 when A and B are 1 and C is 0. So A and B are 1, C is 0. I want a 1 right there. And I want a 0 everywhere else. Well, guess what? This truth table actually corresponds to a case where we have two adjacent rows that we both want to have equal to 1. And so here again, I can look at this and I can say, you know, in these two rows, it's only the values of C and B that matter. I need C to be a 0, and I need B to be a 1, and as long as those two things are true, doesn't matter whether A is a 0 or a 1, the output is still going to be 1. And so I could write X equals, you know, C bar B, or, you know, if I want to keep the order the same, it's the same thing. I could write that, and that's a valid truth table expression for this truth table. And it's better than, you know, doing A bar B, C bar, or A B C bar. So it's simplified. Okay, so what's going on here? When you write a truth table, if you happen to have adjacent rows where the value is 1 in both of those, right, broken up in groups of 2, you can do the simplification. But it may be possible to do that simplification even if you don't see adjacent rows by rearranging your variables. So we need a trick. We need a way to be able to do this without having to actually write different versions of our truth table and look for these adjacent rows. This is what a K-map is. Okay, so let me draw you a picture of a K-map. And I'll go ahead and stick with this 3-input example, but usually we do K-maps for like 4 input variables. Okay, so we're going to draw a rectangle, and we're going to break it in this case into 8 squares. Now you can draw this as a wide rectangle or a tall rectangle, and I'm going to label A going up and down. I'm going to label B and C going across. And A can be a 0 or a 1, and BC can be 0, 0, 0, 1, 1, 0, or 1, 1. Okay, really important detail. When you label these, you have to do them in this order. Okay, it's not the usual counting order 0, 1, 2, 3. It's actually 0, 1, 3, 2. Okay, that's really, really critical. So I've just got this template. Now I'm going to fill in all of the ones from my truth table. So, for example, I want a 1 where A is 0, B is 1, C is 0. So A is 0, B is 1, C is 0. Right? And so I'm thinking of this as, you know, this is B and C, this is B and C. Right? So there's 8 rows in the truth table, there's 8 boxes in my K-map. Okay, so A is 0, B is 1, C is 0. So A is 0 is this top row. B is 1, C is 0. That's one of our ones. And my other one is A is 1, B is 1, C is 0. So A is 1, B is 1, C is 0. That's my other one. And everything else is a 0. I'm not going to bother filling in zeros. We only fill in the ones if we're doing a sum of products. Okay, so let me start jotting these steps down. So step 1, draw an empty K-map. Step 2, label the sides and make sure If you have 4 spots to label, that you do them in that order. And then step 3, fill in the ones. Alright, that's where we're up to right now. Okay, step 4 is what we call cover the ones. So covering the ones means drawing rectangles that contain only ones. Okay, we're going to draw rectangles that cover the ones, that contain only ones and don't contain any of the zeros or blank squares. And there's some rules here. So cover with rectangles. Don't cover zeros. So I can't draw a rectangle like this because that's covering zeros. Sides must have length 1, 2, or 4. So any rectangle we draw, it has to have each side having a length either 1, 2, or 4. We can't draw a rectangle with a length of 3 on a side. Okay. Bigger rectangles are better. And fewer rectangles are better. We need to cover all ones, and multiple covers are allowed. And we'll do examples, and this will hopefully make it clearer. But using these guidelines, what rectangle would I draw here? Probably the best I can do is just a big rectangle right here. Okay, it's a 1 by 2, so it satisfies that. I haven't covered any zeros. It's the biggest rectangle I can do. It's the fewest number of rectangles I can do. I've covered all of the ones. This is a good covering. Okay, so step 5, write a product term for each rectangle. And then step 6, sum those. Okay, how do we write a product term? Take a look at this rectangle, and first we ask, what's the value of A at each point in this rectangle? Well, at this point, A is equal to 0. At this point, A is equal to 1. So A can be 0 or a 1. What about B though? At this point B is 1, in this box B is 1, B is always equal to 1. And what about C? In this box C is 0, in this box C is also 0, so C is equal to 0. Okay, the product term we write is the following. Since A is 0 or 1, we don't include A. Okay, so A, don't include. Since B is equal to 1, we use B. Since C is equal to 0, we use C bar. And so the product term corresponding to that box is just B ended with C bar. And if we had other rectangles, we would write product terms for those, and in the end we would sum those together. Since that's our only rectangle, that's our only product term, so our expression x is just equal to BC bar, which was what we got from the truth table analysis. I'm going to add one more thing to this list of covering the ones, which is asteroids. Anybody here play asteroids? So we'll see what asteroids does for coverings. So let me just cover some K-maps just to practice. So let's go with 4 input variables. So there's a K-map. So let's just suppose our inputs are A, B, C, D. And let me throw some ones down here. So there's some ones. All right, and we want to, use these rules to cover these rectangles.
How do you decide where you put the ones?
So there's a truth table that I haven't shown you here, but there would be a truth table which where A is 0, B is 0, C is 1, D is 0. The output was a 1. So normally...
Okay, so it's the outputs?
Yeah, so normally we're starting with the truth table, and wherever there's a 1 in the output, you fill in the corresponding box.
Okay.
All right, so we've done that, and this is the K-map that we've come up with. And we want to find rectangles that cover these. They only cover the ones. We don't cover any zeros. So, you kind of start with the outliers maybe. There's a 1 sitting right here. Now, I could cover that with a little 1 by 1 rectangle. That's perfectly fine. But I could also cover this by drawing a 2 by 1 rectangle. And bigger is better, right? Bigger rectangles will get us a better solution. Now, I could draw a 3 by 1 rectangle, but the lengths have to have, length 1, 2, or 4. We can't have a side with length 3. And I can't do a 4 by 1 rectangle because I'd be covering a 0 up here. So this is the best rectangle I can do that covers this one, and it also happened to cover this one. Alright, well this one right here I could cover with a rectangle like this, or I could cover with a rectangle off to the side. And it's really not going to make any difference, but I'm just going to go ahead and cover this off to the side. Right, and that's a 1 by 2, that's a legal rectangle, I'm only covering ones, but I've picked up 2 of these. I can't make it any bigger. Okay, but I've covered 4 of my ones now. Now this rectangle right here, this one right here, I could cover it with a 1 by 1. I could do a 2 by 1 and pick it up like that, but when you play asteroids, right, when something goes off the end, it wraps around to the other side. Same thing with K-maps. This edge is connected to the top edge, and this right side is connected to the left side. So I can actually make a broken rectangle that looks like this. Right, and that's a single 2 high, 1 wide rectangle that's covering both of those ones. And that's legal. So that's what I mean by asteroids, the ends wrap. And that's a complete covering of my rectangles, my ones. So I would write a min term, a product term corresponding to each of these. Let's just pick out this rectangle right here. So in this cell A is 0, and this cell A is 1, so A equals 0 or 1. In this cell B is a 1, in this cell B is a 1, so B is a 1. In this cell C is a 0, and here C is a 0, so C is a 0. And in this cell D is a 1, and down here D is a 1, so D equals 1. And so to write the product term corresponding to this rectangle, I don't use A, because it can be 0 or 1, it doesn't matter. B has to be a 1, C has to be a 0, D has to be a 1. There's the product term for that rectangle. And I'll write one for this, and when I sum them together, that's the expression that corresponds to the truth table that generated this. Alright, so I'm going to do a video later on today and go through this again and also show you how we deal with don't cares, how this works with product of sums, and how you get this from the truth table. Okay, so I'll do a fairly extensive K-map video after class, and I'll post that up tonight. Alright, any other questions? Alright, cool. I will call it a day then, and I will see you next time. I forgot to record all of that. Oh, no, I didn't. That's recorded. Okay, cool. See you next time.